Okay, let's calculate the electronic contribution to the thermodynamic properties. And for that, we're going to calculate the electronic molecular partition function. Now, you may have noticed as we went from translation to rotation to vibration, the energy gap was increasing and the characteristic temperatures for those motions were increasing to the point where when we got to vibration at room temperature, we were not able to use the classical approximation. And in fact, actually, it was only the ground state that mattered the most, and maybe one of the two excited vibrational states that went into the partition function. Now that we've reached the electronic motion, the energy gap is so much larger than in the case of, say, vibrations, that we won't even need to use the excited states. We'll be able to just stick with just the ground state when calculating the molecular partition function. Now, there may be some exceptions where we have some low-lying excited electronic states, but for the most part, we'll just stick with the ground state for calculating the molecular partition function. So let's start out with the general expression here then, and we'll rearrange this by pulling out the ground state degeneracy and energy, and I'm going to redefine the ground state energy as D naught and this expression here, and I'm going to have a summation that is going to involve the excited states, where I have now written a delta E, where delta E is the energy of the excited state minus the ground state energy, which I've redefined as D naught. And at room temperature, or even a few hundred Kelvin, we don't expect this part to contribute, and that we're just going to have the ground state term. But if we need to include some excited state terms, then they're going to have this form here, and we would just continue with this summation like this. Now, when we're working with monatomic gases or working with individual atoms, it's actually convenient to just redefine the electronic ground state for the atom to just be zero. It doesn't affect our heat capacities or entropies. It does cause a constant shift in our thermodynamic potentials, like Gibbs energy or free energy, Helmholtz energy, but it's not going to really cause any problems for us in any of our thermodynamic calculations by doing this. And that will simplify things, because then we'll just need to know the degeneracy of the of the atom's ground state, electronic ground state. When it comes to molecules, we have the same expression here. Nothing's changed here, except now this is the molecular ground state. This is the molecular ground state degeneracy. But if we're going to redefine the D0, we need to do it in a way that allows us to calculate thermodynamic properties for thermodynamic processes. So if we want to have a chemical reaction and we want to calculate an equilibrium constant or something like that, we have to use a D0 that is sort of uniform across all the reactants and products that we're using. In other words, we can't just take D0 for every molecule and define it as 0 for that molecule, because that molecule relative to another molecule's ground state are not going to be the same. So we need to pick then one way to define D0 so that when we calculate the delta G for a reaction or delta S for a reaction, we'll get the correct result. And the way to do that is to define D0 for the molecules as the energy relative to the atoms in the molecule that are infinitely far apart and at rest at 0 Kelvin. So this is the zero, we're assigning the zero potential energy to all the atoms in the molecule infinitely far apart, and then as those atoms come together to form the molecule in its electronic ground state, that lowering in the energy is defined to be D0. Okay, so that's the way we're going to do it. And with that definition, then it becomes this expression here, which is this D0, dE is just the energy at the bottom of the potential energy, but then remember there is a 0 point energy. That's the true dissociation, is not from the bottom of the potential energy well, but from the vibrational 0 point energy. So we have to add those terms into this expression here. But this is how we're going to define uniformly for all our molecules their D0 relative to the infinitely far apart atoms that make up that molecule. And again, that's going to shift the potentials, but it won't shift the entropies or the heat capacities. So once we have done that, then we can go back to our expression. Let me just go back to this expression here, and we can put it into our expression for the molecular partition function and calculate the canonical partition function. And then expanding all that out, it becomes this expression here. So now we have the term that involves the degeneracy of the ground state, then our definition for the D0 term, and then the contributions from the excited states are going to show up here. Now, if I calculate from this all of the thermodynamic potential contributions, then I have the Helmholtz and Gibbs energy, the entropy, the internal energy, and enthalpy, and then the heat capacities all come out like this. And you can see that if we can neglect the excited states, then we're really just going to have that term there. We're just going to have that term there, and this term, and these guys are actually all going to go to 0 here. So this is what we're going to have if we just include the first excited state along with the ground state. If we just got rid of the excited state and we just had the ground state, this would be our partition function, and these simplify quite a bit down here, and you can see that there's actually no contribution to the heat capacity, as you would expect if there's only the ground state that gets populated. Okay, now let's take a look at some of the electronic state degeneracies. Whenever you have a molecule that's in its ground state, or an atom in its ground state, and it's a closed shell ground state, then we know that the degeneracy was going to be 1. But more generally, you can just look at the term symbol for the atom or the molecule and figure out what the degeneracy is going to be. So whenever you have an atom, you can just look at the symbol. So in that case, you have the little subscript J here. So from that subscript J, you know the degeneracy is going to be 2J plus 1. It's that straightforward. Whenever you're looking at a linear molecule, we talked about that in the last chapter, then you would look at this subscript here where you have lambda plus m sub s. So adding those two together, we define a quantity called omega, and we take the absolute value of lambda plus m sub s, and your degeneracy is going to be 2 omega plus 1. If you're dealing with a nonlinear molecule, we didn't talk about their term symbols, but the term symbols actually, just simply looking at the letter is enough to get the degeneracy. So if you have a letter A or B in the term symbol, then the degeneracy is 1. If it's E, it's 2. If it's T, it's 3. If it's G, it's 4. If it's H, it's 5. So it's relatively straightforward to just look at the term symbol and extract out from that the degeneracy of the electronic level. So let's look at an example where we calculate using the electronic partition function. So let's take a system where we have chlorine, where its ground state is a doublet P3 halves, and its first excited state is a doublet P1 half, which lies 882.35 inverse centimeters above it. So this is a case actually where we have a relatively low lying state. Most of the time it's not going to be like this, but let's just do this because it's a little bit more illustrative calculation of how this works. So we want to calculate the entropy and the heat capacity for 1 mole of chlorine at 500 Kelvin. So we'll take our full entropy expression here, which includes the one excited state, and we have to calculate or work out what the degeneracy is, calculate this ratio for the first excited state energy and the ratio of the degeneracies. So for doublet P3 halves, the degeneracy is 4, so 2 times 3 halves plus 1 is 4. And for doublet P1 half, the degeneracy is 2 times 1 half plus 1, which is 2. So the ratio of the degeneracies is 4 over 2, which is 2. So if we calculate the ratio for this energy here, which is just constants times 882.35 inverse centimeters divided by kb times 500 Kelvin, we get this. So now we have our degeneracies, the ratios, and this ratio here, we can substitute them into this expression, and we calculate out fully the entropy, which comes out with entropy over R as 1.52 moles. We plug in the gas constant here, and we get 12.6 joules per Kelvin. So there's a simple calculation of the entropy. Let's look at the heat capacity. Similar, it's a complicated expression here, but it just involves the first excited state. There's no contribution from the ground state. So we've already calculated these ratios here, so we'll just go ahead and plug in the numbers for the ratio of the degeneracies and this ratio for the energy over kBT, and you get 0.236 moles for the heat capacity over R, but multiplied by R, you get 1.96. So that's actually, fairly sizable considering the fact that if we couldn't access the first excited state, the degeneracy, only had the degeneracy of the ground state, the heat capacity would be just 0, right? So in this case, then we're getting a heat capacity of 1.96 because of that population of that first excited state. Let's look at another example of a molecule. So this is, say, the NO molecule, which actually has an unpaired electron, and it has a ground state that's a doublet pi half, and the first excited state lies even closer, 1.23.8 inverse centimeters. It has a term symbol of doublet pi 3 halves. And if we wanted to do the same calculation there of the 1 mole of the gas at 400 Kelvin, we would take our entropy expression again, just like before, and we'll look at the terms, and we see that for the ground state, which has a doublet pi half, from this half here, we know that we can do 2 times half plus 1 is 2. And for 3 halves, the excited state, it's 2 times 3 halves plus 1 is 4. So the ratio is 2 over 4, or 1 half. Then we calculate the ratio for the energy over kBT, which is this term here, which is 0.4453. Plugging those in to the entropy expression, we get this expression here. You can work this out yourself. You should get 1.77 moles, which is the entropy divided by R, multiply times R, and you get 2.26 joules per Kelvin for the entropy contribution here. Okay, so remember there's an entropy contribution from the ground state, which comes from this degeneracy term, and then this is the contribution from the excited state. If we wanted to calculate the heat capacity, remember the heat capacity is from the ground state alone. If there was no excited state, the heat capacity would be 0. So it all comes from populating this first excited state, and we have calculated all these ratios, plug them into here, and you get 0.236, which is the heat capacity divided by R, but if you multiply times R, you get 1.96. So this is what you would get if you include this excited state, which is actually considerable. If you would ignore that, you would have been off by 1.96 because you would have had 0 if you ignored the excited state. So there we go. We have a couple calculations. As I say, it gets a lot easier if you have higher lying excited states. All you need to do is worry about the ground state, in which case you're just doing calculations with these numbers here, and all you need is the degeneracy and this D0 value to calculate any of these properties. So that's it for this lecture.